Okay, so let's move on to entropy. And this is fascinating. So because we don't have constant, we are not in the canonical ensemble, energy is no longer constant. So to compute entropy, we need to count all the states of different energies, right? So we need to count all the states, or all with with different energies. And what we should do is that we should weigh those by the probability of that state. Okay. So this is a cryptic statement. Let me just be more specific. So we're going to use kind of a trick to do this. So suppose we have our system S. To calculate its entropy, I'm going to take W copies of it. Okay. So where W is a large number. So I take a large number of copies. So this is, we may not be able to do it in principle, but in reality, but in principle, we can think of it. And then, what happens is that if P alpha was the probability that the system was in the energy state E alpha, then the number of systems which have energy E alpha is going to be just given by P alpha times W, right? Do you agree? So let me draw a picture. I mean, it's not necessarily something that is you may find helpful, but I found it helpful in trying to understand this. And the picture is I have W copies of my system. Sorry, the lines are not parallel. So suppose that we have W copies of our systems, and then suppose that, okay, let me just do a bit more subdivisions, okay, just to make the picture a bit prettier. And suppose that we have these are the systems, number of systems which have energy E1. Okay, so this is E1. So the number of systems with E1 is P1W, right? And suppose this is the number of systems with energy E2. So this is E2, and this is going to be, say, P2 times W. And let me take other colors. And then suppose that this is the number of systems, say, with energy E3. So this is P3W. And then this is the number of systems with energy E4. So this is P4W. And I'm going to cut things short. And this is the, sorry. And this is the number of systems with energy E5. And this is going to be P5 times W, okay?
So basically, it's like as the number becomes really large, the proportion tends to imitate the percentage chance of
exactly. Yeah, that's it. Very easy, right? So now what we want to say is that given W systems, how many ways can we, and given W system, given the probability distribution P alpha, which is given by the Boltzmann distribution, how many configurations of this type do we have? And that's the total configuration for W systems. Let's count that. So let's count the first energy state. So, we can have W, the first, we can choose the first system W ways. We can choose the second system in W minus 1 ways, dot, 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 W minus, W minus, say, P1 plus 1, right? You agree?
Yes, sir.
But the thing is that all of these systems are, there's going to be like we are overcounting, right? Because this guy can go here, and this guy can go here, and this guy can go here, and they're all the same system. So we have to divide by P1W factorial.
Sir, I think on the upper portion of the fraction you missed a W. There should be a W after P1, I suppose.
Yes, you're right. Yeah, sorry about that. Yeah. So there should be a W P1 plus 1, right? So now what we have left is that the system that is left, we can put them in another state P2, another E2, and then so on and so forth until we get to 1. But each of these things, we have to divide by the overcounting factor. And suppose we had M configurations of energy, M energy values. So this is the total number of configurations we're going to have. And if I write this, this is going to be factorial of W divided by multiplication of alpha, P alpha W factorial. Okay. Where alpha goes from, say, 1 to M, where M, well, that's the number of energy states. That can be infinity, I don't care about that right now. Okay, so this is important to understand this, and if just think about it as well, if you're not used to combinatorics, which I am not always, so I have to think about these things. So okay, now what we do is that we use Stirling's approximation formula. So we use Stirling's, and then ignore the constant terms, and then we get the entropy of the W systems is going to be KB times log of omega, and this is going to be, if I use Stirling, it's going to be approximately KB of W log of W minus, now the multiplication here becomes sum, right? Because we're taking the log, so sum, and inside the sum we have P alpha W log of P alpha W minus P alpha W, right? So I've used Stirling twice. So now I can just do some algebraic manipulations. So it's KB, and then the first term becomes W log of W, and we have a W, and then we can factor the W out from here. Then we have minus of W, and we have a sum over alpha. The first term is P alpha log of P alpha, and then there's a multiplication here, so we can write that as minus W times sum over Yeah. Hang on. Right. Sum over P alpha log of W, right? And then we have a term which is plus W sum over alpha P of alpha, right? Yeah. Now this is one, so I should not, should not. This is just one. This is also one, and if I do this, I get that this term will cancel this term, and this term will cancel this term. And therefore, we get omega is minus kb of w of sum over alpha p alpha log of p alpha. But we know that when we combine systems, independent systems, their entropy is additive. So we have combined W systems. So the entropy per system, so this is W system, the entropy per system is going to be just minus of KB sum over alpha P alpha log of P alpha. And this is the entropy. Sorry, why am I using the, omega here? You guys should have said something. This
I
is
was waiting to say.
good, very good. And this is S. Good, very good. And this is S. So this is the entropy of the canonical ensemble, and this is known as Gibbs entropy formula. Okay, and this is a remarkable formula, and this is a beautiful formula which also has applications in quantum mechanics as well as in information theory. Okay, so let me just make a couple of comments before I open it up for questions. One is it's Gibbs entropy. The other thing is that if one of the state has probability 1, then of course the entropy is 0, right? Because log of 1 is 0. But if some of the state may have no probability of being occupied, for those states, log of 0 is minus infinity. For those guys, what we do is that we say that P log of P alpha goes to 0 in the limit where P alpha goes to 0. Because even though log of P goes to minus infinity, this guy goes to 0 much more rapidly, and therefore the product goes to 0 very rapidly. So for those states, where there is the probability of it being occupied, they don't make any contribution to the entropy. Okay? And for those states for which P of alpha is less than 1, the contribution to entropy is positive, of course, because log of P alpha is less than 0, and because of the minus sign here, the contribution is positive. So the entropy is positive. Okay, so this is all I have for today. And this is, I think this is a very, very beautiful formula, and I like the derivation of it. It is partly adapted from David Tong, partly from other places. And so, yeah, let's have some questions, okay?
So on the SW formula, wouldn't the summation of alpha P alpha go to 0?
Sorry, which one?
SW is equal to KBW summation of alpha P alpha. Wouldn't that summation of alpha P alpha go to 1?
No, because you're multiplying it by log of this. It's not, you're not factoring this out.
Oh, okay.
Yeah, it's weighted by this factor, right? Over here, because P alpha was just occurring by itself, you could use 1. But over here, you can't because of this factor. Any more questions?
In the expression above, I think there was a W missing in the logarithm, or was that like separated in this? Yeah,
It
this
was
line.
separated. Yeah.
Oh, I see. It was separated.
Yeah, it was separated, right? Yeah. This is how it got separated.
All right.
Because it was PW, so we separated it out. And that's what canceled this thing. Okay, any more?
So the W can come out of the log.
Which W?
Log of P alpha W. The W can come out of the log.
No. It just I wrote this as log of AB is log of A plus log of B. And the first term is this term, and the second term is this term. This is the A term, and this is the B term. Okay.
Okay.
So I wrote this term in terms of this guy and this guy.